Hello and welcome to the second installment of solving exponential equations. This one's going to be a little bit different because they're not going to end up being same bases. And you have to have some information about how to solve log equations in order to do this. So if you're not familiar with log or the idea of or the word log freaks you out, you're not ready for this lesson yet. So, assuming that everything's cool with logs, there's two methods of doing this. One is to rewrite the equation as a logarithmic equation. This works if only one of your bases is raised to a power with a variable in it. It's very easy to do it that way. We're going to see two examples of that. And then the second method is if it's not as easy, you can take the log of both sides using what would be an appropriate base. And again, you'll see how we determine what the appropriate base is, and we have a couple of examples of that. All right, let's get right to it. So here we have 2 raised to the x plus 3 is equal to 7. So it's an exponential equation. We can't get like bases with 2 and 7. So what we can do is rewrite this exponential equation as a log equation. When you rewrite as a log, your base in your exponential becomes the base of your log equation. So this is log base 2. And because logs and exponentials are inverses of each other, what used to be the independent variable is now the dependent variable. What used to be the dependent value is now the independent value. So it would be log base 2 of 7 is equal to x plus 3. And to solve for x, we would then just need to subtract 3 from both sides. So we'd have log base 2 of 7 minus 3 is equal to x. So that would give you a value that this is exact. If you wanted to use your calculator, you would get a decimal approximation, but this is the exact value for x. Okay, we'll do another one, this time with a base that's not as popular for some reason, but good old-fashioned e. Used a lot in mathematics. Here we have 2 times e to the 5x is equal to 4. We can't quite rewrite it as a log equation yet because we don't have it in the form of base power answer. Here we have it as coefficient base power answer. We need to get rid of that coefficient. We could do that. We can divide both sides of the equation by 2. We'd end up with e to the 5x is equal to 2. Now we have base power answer. We can rewrite this as a log equation. All right, the base of my exponential is e, so the base of my log would be e. Anytime you have a base with a log of e, it's going to be a natural log. Okay, remember that the 5x and the 2, or the dependent value and the independent value and the dependent value are going to switch. So instead of the log of 5x, it'd be the log of 2, because that's what happens in an inverse, is equal to 5x. Okay, so the natural log of 2 is equal to 5x. We divide both sides by 5, so we get 1/5 of the natural log of 2 is equal to x. Or if you like seeing it as the natural log of 2 divided by 5, feel free to do that as well. All right, so that's the first method. Is if you have it in the form of base power answer, you can rewrite it as a log equation using what you know about inverses. Okay, what happens if it's not as easy to do that? You have 2 bases raised to the power. You can still do it that way, but what most people like doing is taking the log of both sides of the equation. Much like raising both sides of the equation to a power, or rooting both sides of an equation, you can take the log of both sides as well. So let's choose an appropriate base. So I think that the base that I want to use for this one is going to be base 5, because it's got a more complicated exponent, so I'm going to use log base 5 for both of these. So I'm going to take log base 5 of 4 to the x is equal to log base 5 of 5 to the x minus 3. Now the reason that you want to choose one of these as being your base is because anytime you compose a log function and an exponential function where the bases are the same, so in this case the base of my log is 5 and my exponential base is 5, what ends up happening is these inverses quote unquote undo each other, and you end up with just the exponent in this case, which would be x minus 3. On this side, not so lucky. We have an x in the exponent, which is not good, but if you remember one of the rules of logs is that if I have an exponent in a log function, I can rewrite it as a coefficient. So x log base 5 of 4. And this is multiplication. Okay. We need to get our x's on the same side, so let's see, subtract this from this side and then add the 3 to the other side. So, well, yeah, let's do it that way. So we're going to get 3 is equal to x minus x log base 5 of 4. We need to factor out the x from everything so we can get x isolated. So it's 1 minus log base 5 of 4. And then we can divide both sides by 1 minus log base 5 of 4. And that is the value of x. This is exact. If you wanted to put it into your calculator, you get a decimal approximation, but this is the exact value of x. Let's look at one more example like that. Here I have 2 to the x is equal to 10 to the x plus 7. Again, I think I'm going to use a log with a base of 10 when I take the log of both sides, because this has a more complex exponent. If they're the same level of complexity, it doesn't matter. So let's do log base 10, which is the common log of 2x, is equal to log base 10, which is the common log of x plus 7. Again, the common log has a base of 10. My exponential has a base of 10. So what happens with these inverses is that they will end up undoing each other, and I'll just get x plus 7. We're going to use the power rule for logarithms. I'm going to rewrite this as x times the log of 2 is equal to x plus 7. Let's see. In this case, this time, and it doesn't really matter, I'm going to subtract the x from both sides. So I'm going to have x log of 2 minus x is equal to 7. Factor out that x from both of them, so I have log of 2 minus 1 is equal to 7, and then divide by that. So we have 7 divided by log of 2 minus 1, and there is your solution. Let's do one more with equally complex exponents. So we have something like x minus 1, x plus 2. Okay, let's use log base. So in this case, it doesn't matter. I'm going to use log base 4 just because we've used log base 5 before. So log base 4 of 4 to the x minus 1 is equal to log base 4 of 5 to the x plus 2. So these bases are the same. Base of 4 in the log, base of 4 in the exponential. So this just becomes x minus 1. Over here, they're not the same base. 4 and 5 are not. We still need to use the power rule to get that x plus 2 out of the exponent, so it would be x plus 2 moved to the coefficient of log base 4 of 5. Okay. Notice it's in parentheses. That's very important because if you don't put it in parentheses, you're not saying that the entire quantity is being multiplied by the log, and it is. Okay. So when you move your exponent, keep it in parentheses. Alrighty, let's distribute this because we need to get the x alone on one side, which means we need to get it outside of those parentheses. So x minus 1 is equal to, it'd be x log base 4 of 5 plus 2 log base 4 of 5. Okay, we need to get the x's on the same side, so I'm going to subtract this term from this side, and this has no x attached to it. I'm going to add it to this side. So we're going to get x minus x log base 4 of 5 is equal to 1 plus 2 log base 4 of 5. Okay, factor out that x from both of these terms. We get 1 minus log base 4 of 5 is equal to 1 plus 2 log base 4 of 5. And then just divide out by all that stuff. So x is equal to 1 plus 2 log base 4 of 5 divided by 1 minus log base 4 of 5. Okay, and there you have it. That is the value of x that would make this equation true. You can use your calculator to find the decimal approximation, but this is the exact value. And that is how you solve exponentials when you can't find a like base.